Hi, welcome back to my channel. My name is Gina. In this video, we are going to look at an example on rotational dynamics. Before we start the example, let me do a quick recap on the angular quantities. In linear kinematics, we have position, velocity, and acceleration, and we denote them as x, b, and a. In rotational kinematics, the position is now the angle theta, which is the linear displacement over the radius of the circle. And the angular velocity is omega, which is linear velocity divided by radius. And linear acceleration is alpha, which is linear acceleration over r. And the linear inertia, the resistance, is the mass. Its angular quantity is the moment of inertia, capital I. The moment of inertia of an object depends on its shape. And the force in linear dynamics, by Newton's second law, it is mass times acceleration. So similarly in rotational dynamics, the angular quantity is tau, the torque, and it is also the inertia times acceleration, but with angular quantity. So that is moment of inertia times angular acceleration. And the kinetic energy in linear quantity is half m times speed squared. Similarly with rotational kinetic energy, it is half times moment of inertia times angular speed squared. And the last quantity, the momentum. In linear dynamic, it is mass times velocity. So the angular quantity, it is also the inertia times velocity, and we call this the angular momentum. It equals to moment of inertia times angular velocity. Let's look at this Edwin machine. We want to find the acceleration of blocks. Here the spring is attached to two blocks. The one on the left is 10 kilograms, the one on the right is 15 kilograms. The mass of pulley is 5 kilograms. Let's start with drawing the forces on the objects. On the 10 kilograms, there is the gravity force that is pointing downward. Let's call it Fg1. And there is the tension force that is pointing upward. Let's call it Ft1. On the 15 kilograms, there is also the gravity force and tension force. On the pulley, there is tension forces, Ft1 acting on the left and Ft2 acting on the right. And the pulley also has mass, so it has gravity force and is attached to another string, so there is another tension force. Now let's define the positive direction. For the 10 kilograms, I'm going to define positive as upward, and for the other block, I'm going to define negative as positive. For the pulley, I'm going to define clockwise as positive. And since everything here is attached, so they'll have the same acceleration, which means acceleration on the 10 kilograms equals to acceleration of the 50 kilograms, and this equals to the tangential acceleration of the pulley. And I'll just call them A. Now let's use Newton's second law on each of the mass. Let's start with the 10 kilogram. So by Newton's second law, F net equals to mass times acceleration. We define upward as positive, so F net is tension 1 minus gravity 1, and this equals to mass 1 times acceleration. Let's isolate for the tension. So it equals to 10 times A plus 10 times G. Let's call this equation 1. Now let's look at the 15 kilograms. Similarly, Newton's second law says F net equals to mass times acceleration. We define positive as downward for this mass. So F net is gravity 2 minus tension 2. And this equals to mass 2 times 8. Again, let's isolate for tension. So tension 2 equals to 15 times G minus 15 times 8. And let's call this equation 2. Now let's look at the pulley. Here, instead of finding the net force, we are going to find the net torque. And net torque equals to moment of inertia times angular acceleration. Moment of inertia for a disk is half times the mass times radius squared. And angular acceleration is the tangential acceleration over r. So if we substitute this into this equation, net torque equals to half times mass times the radius times tangential acceleration. And since the gravity force and the third tension force is acting on the axis of rotation, so they will not contribute to the net torque. So the only forces that will contribute to the net torque are the first and the second tension forces. And we define clockwise as positive. So the second tension force will have a positive torque and the first tension force will have a negative torque. So net torque is the radius of pulley times the second tension force times sine of 90 minus radius times the first tension force times sine of 90. And this equals to half times mass times radius times tangential acceleration. Sine of 90 equals to 1. And we can cancel out the radius of the pulley on both sides. So we are left with second tension force minus the first tension force, and this equals to half times ma. And the mass of pulley is 5 kilograms. And let's call this equation 3. Now we get 3 equations with 3 unknowns. The unknowns are the first tension force, second tension force, and the acceleration. So we have a closed system. To find the acceleration, let's substitute equation 1 and equation 2 into equation 3. So we get 15 times G minus 15 times A minus the first equation, 10 times A plus 10 times G. And this equals to the right hand side of the third equation, 5 over 2 times A. So we get 5 over 2 plus 15 plus 10 times acceleration equals 25 times G. We isolate for acceleration, we get A equals to 8.91 meter per second squared. And that is the end of the video. If you like my videos, please like and subscribe, and I'll see you in the next video.